All right, hey guys, welcome to yet another graduate seminar. This is Mohammed. He'll be talking about his master's thesis. Good luck or enjoy.
Okay. Okay, let me fix this. Okay, hello everyone. So let us start. So this work is a joint work with Mohammed Sadiq from Sabancı University. This is my master university in Turkey. Okay, so the main objective of this project is mainly this. This is the main objective. So the objective is constructing, or the construction of irreducible polynomials of arbitrary high degree. Now, this technique, we need to use actually iterative techniques. So we want like a sequence of irreducible polynomials. Okay, so one of the ideas, or one of the ways we can do that, is by composition. So you can start f, and then you can start f of f, and then f of f, and so on. But here is a question. Under what conditions is the polynomial f of g irreducible? So the thing is, not the composition of any two polynomials is always irreducible. Simple example, I can tell you like, okay, f of x is x, let's say, minus 4, and f of x squared is just x squared minus 4. So even if the polynomial outside is irreducible, we still have a problem. Now, the solution to that is easy.
Shouldn't that have been like x minus 2?
What?
Are we in Q? Yeah,
What?
What's our field?
Q, yeah,
Q?
yeah.
Yeah, so that should have been like x minus 2, so that square root of 2 wasn't in there. Because you use 4.
Yeah.
That
So
would have been fine.
So like this. So x minus 2, x plus 2, like this.
Exactly. That is,
Yeah. This is the
okay.
thing. Okay, so this is the situation. Now, we do have a solution for that. It's called Capelli's lemma. So let f and g be in Kx, and this is a field. We have f of g is irreducible over K if and only if f is irreducible and g of x minus alpha is irreducible over K alpha, where alpha is a root of f. Okay, so now if I want to check the irreducibility of every single one of these, this condition should be satisfied. So this is actually the problem in our case. Okay, now there is a formal way to deal with this. Now, in a matter of fact, for the rest of the talk, our case should be Q. We will be working over rational numbers. So let me define something now. So let me define a discrete dynamical system is a set A along with a self-map phi from A to A. We define the nth iterate of phi, namely phi n, as this. So the thing is, I'm composing phi with itself n times. And conventionally, phi of 0 is the identity map. Now, in our case, phi is a polynomial over Q, and of course, A is equal to Q. Okay? So, yes?
Good question. So, over here, alpha, does it belong to the field K? Or does it have to be something like
No, it cannot belong to the field K because F should be itself irreducible. So alpha, you can think about it as it's in the closure.
Okay, just an element in the downgrade portion. Okay.
Yes. Okay.
And it has to be outside of K, right?
Yes, because if it's inside K, F will be reducible, so we'll have a problem.
Sure. Okay.
Yeah.
Okay.
So in this case, A will be Q. Now, so instead of talking about this, I can just say that this is F of n. Okay? So I will talk this about, I will say that this is the first iterate, second, third, and then nth iterate. Okay. So let's define something relevant now. Now, we can have the case that F is irreducible, and all of these are irreducible for any n. So again, if let F be in Kx, we say F is stable or dynamically irreducible if Fn is irreducible over K for all n in n. Okay. Now, so do we know some of the dynamically irreducible polynomials? In a matter of fact, yes. Let me give some examples about these. So for example, polynomials satisfying, now I am like, so let's talk about Q for a minute. So polynomials satisfying the Einstein criterion. Now, of course, this does not work over any Q, like we can talk about, because we can define it in general in a commutative ring with unity, with prime ideals, so fine. What else? For example, this was proved by, or I will not say proved, it's a little bit obvious. This was noted by Uduni in the 80s, who was the first person to study like dynamical irreducibility. He also proved that x squared minus x plus 1 is dynamically irreducible. this has a, this is like a 2-page proof, which is a little bit non-trivial. Then we do have another major result by Boston and Jones. It says the following. This is for quadratic polynomials. So if you have a polynomial f of x is equal to ax squared plus bx plus c in some field kx, and gamma is negative b over 2a, then if f is dynamically irreducible, then we have negative a of f of gamma, and then a of f2 of gamma, and then a of fn of gamma for all n greater than or equal to 2 is a non-square in K. So is it clear, or the marker is okay. So let us. So the thing is, what Boston and Jones proved is that if we have a polynomial which is dynamically irreducible, so all the iterates are irreducible, and it's a quadratic polynomial over a field, then yeah, okay, thank you. Then this and afn for n greater than or equal to 2 should be a non-square in K. Okay? Now, the converse is true if K is a finite field. Okay? So for example, if I let us erase this and give you like a quick example about this theorem. So if I tell you f of x is equal to x squared plus 1 into over the finite field with 3 elements. Now, here my a is equal to 1, my gamma is equal to 0. Then negative of f of gamma would be 2, right? And fn of gamma is equal to 2 for all n greater than or equal to 2. And 2 is not a square.
Sorry, so Fn is n compositions of F?
Yes.
So F, going up here is the same thing as 5 over here?
Yeah. So as I mentioned here, if this is satisfied, if it's dynamically irreducible and it's so this will be satisfied. And if it's finite field, it's an if and only if statement. Okay. Now let's ask another question. So if Fn is irreducible for some large n, does this imply that f is dynamically irreducible? Now I will just use di for dynamically irreducible, just to be a little bit more efficient. So the thing is, if I try to see the irreducibility of the some iterates, will I be able to conclude that all the iterates are irreducible? As a matter of fact, there is no like a clear answer for that for all the polynomials. There is for some of them. I will mention that in a second. But just to give you an idea how complicated is this question, let's take this same polynomial. So x squared plus 1, but over the finite field F43. So with the if you do like test irreducibility here, you will find out that F, F2, F3, 4, F5 are irreducible, but F6 is reducible. So it is actually a problem, and also as you see the degree, it grows exponentially. So this is another problem with using any software, that after a couple of iterations you'll not be able to use softwares. So you have to use algebra. Okay. So now here is another question. Let me just define something a little bit quick. If f till fn minus 1 are irreducible, but fn is reducible, we call f n newly reducible. Now, there are some papers in the literature about 2 newly and 3 newly reducible. Now, this is probably one of the first examples about 6 newly reducible polynomials. So, now if the polynomial itself is newly reducible, can, again, we do something about constructing irreducible? Can we get irreducible polynomials from that? Okay, in a matter of fact, there is another technique that we can use, but let me do another definition. Okay, now let Kn be the number of irreducible factors of Fn. Okay, so in this case, Kn is just, I look at the nth iterate, and then I see how many irreducible factors does it have. Now, if Kn is less than or equal to C for all n, we say F is eventually stable. Okay? Okay. Now, if C is equal to 1, then what? Then F is dynamically irreducible. Okay? So, again, how do we get irreducible polynomials from that?
You have a definition of stable that involves being irreducible and one
reducible iterates, yes. But the thing is, the number of reducible iterates should be bounded, regardless of n. Okay, so let me state another definition. We say G is F stable. Now, I don't need to define that G is a polynomial over K and F is a polynomial over K. It's already understood now. Now, if I don't really mention anything about Q, then this can, of course, work for any field. Now, we say that G is F stable if G composed with Fn is irreducible for all n in n. So what do? We might have Fn not to be irreducible. But whenever I compose G from the left, I will always have an irreducible polynomial. So this is actually a sequence of irreducible polynomials in this case. Now, if f is f stable, then of course f is dynamically irreducible. So whenever I adjoint f to any iterates of f, it's irreducible, then it is dynamically irreducible. Now, what is the link between this and this? Now, suppose that I do calculate for some polynomial f that the maximum number of irreducible factors that any iterate can have is c. It's bounded above by c. And then I am so lucky that, let's say in the nth iterate, I have g1. Suppose kn is less than or equal to c. Now f is equal to g1. This is like a factorization. So I reach the nth iterate, and then I will be able to factorize fn in the number of reducible factors will be exactly c. So I'll have g1 times gc. Okay? Now next, what will I do? If I look at f of n plus 1, this is exactly fn composed with f, right? Correct? So this would be g1 composed with f times gc composed with f. Correct? Now the number of reducible factors cannot go beyond c. So these has to be irreducible. And actually not n plus 1, I can actually do the same for any further iterates. So in this case, the GIs are f stable. So this is actually the use that we can have defining eventually stable polynomials in this way. Okay. Okay. So, let's talk a little bit about Einstein polynomials. Now, but before, let me maybe tell you the third result about dynamical irreducibility. Now, this is due to Danielson and Fein. If a polynomial of the form x to the n minus b over z is irreducible, then it is dynamically irreducible. So remember when I told you about that, we need to think about if fn is irreducible for some large n, then f is dynamically irreducible. For this family of polynomial, in this actually binomial, if we have over z, if it's itself is irreducible, then all the iterates will be irreducible. So we don't need to do anything. Okay. Now let's talk a little bit about something else. Okay, so let me first remind you of the P-adic valuation. So let P be a prime. Now we are working in Q now, like in Z, or Q, but doesn't really matter. Let P be a rational prime. Now we define the P-adic valuation as follows. It's a map from Z to Z union infinity, such that Vp of A is equal to infinity if A is equal to 0, and it's equal to R if P to the R divides A, but P to the R plus 1 does not divide A. Now, of course, I can extend this to any.
Sorry, what was it's a rational prime?
Mhm.
What is it?
It's a prime in the rational numbers.
Okay, just prime.
Yeah, because if you say, okay, the thing is, if you just say a prime, and then you go to a field extension, this prime might be ramified. It might not be a prime anymore. So
Okay.
that's yeah. Okay. So now for A over B, you can just say that you can define it in this way. So the p-adic valuation of A minus the p-adic valuation of B. We can extend that to Gaussian valuation. Now, in a Gaussian valuation, I'm defining a p-adic valuation of a polynomial. So if you have, let f of x is equal to a polynomial like that, we define the p-adic of the polynomial to be the minimum of the p-adic valuation of the coefficients. And of course, you can see, like, you can actually prove that this is a discrete valuation. So using this valuation, we can define something a little bit more general than the Einstein criterion. So let's do this definition. Let P be a prime. And f in qx. Okay, I have to write it in this case. ai xi I0 to d. If f satisfy the following, yeah.
What's n there again?
Yeah, D. Yeah. Now, the thing is, here we use n for the iteration, but the standard used n for the degree, so that's the problem. Now, if f satisfies the following, so first of all, the p-adic valuation of the leading coefficient is equal to 0. We're working the Einstein criterion now. The p-adic valuation of A 0 is equal to R. The p-adic valuation of AI is greater than or equal to R for I is between d minus 1 and 0, and the GCD of R and D is equal to 1. Then F is called P to the R Einstein, and is irreducible over Q. Okay, so this is actually a little bit of an extension of the Einstein criterion. If you let R to be 1, this condition will be satisfied automatically. Now, we might not be, we might actually use any R which is co-prime with D. So let me give a quick example just to So, for example, if I think about x to the 4 plus 2, this satisfies the Einstein criterion, no problem. Now, if I do this, this is 2 to the 5 Einstein. Okay, because the GCD of 5 and 4 is 1. Now, if I do this, this is again Einstein. P to the P, like 2 to the 5 Einstein. Okay, so it's actually irreducible. Now the proof of why this is irreducible uses a technique called Newton polygons. If we have time, I will talk about it. Okay, now why these are nice? They are nice because it was proved by Ali that P to the R Eisenstein polynomials are dynamically irreducible for any R. Okay? So not only Eisenstein polynomials, if I use any R that satisfies these conditions, then it will be dynamically reducible. Okay, can we extend this? Okay, let me define something now. So I will define something which is a little bit more general, something called P to the R pure polynomial. Now, if you have f of x is equal to, again, such that it satisfies the following. Now, the P-adic valuation, again, of the leading coefficient is 0. Now, this is a little bit tricky. Okay, let me just tell you that the P-adic valuation of the constant coefficient is R. Okay, so what is the similarity between P Eisenstein and pure polynomials? So again, P is a prime, again, no problem with that. Now, the first condition is the same. The second condition is the same. Actually, the third condition is, in the pure polynomials, is more general than the P to the R Eisenstein. So in the P to the R Eisenstein, I am explicitly allowing this to be greater than or equal to R. So you'll have P2 of AI over D minus I will be greater than or equal to R over D minus I, which is always greater than R over D. So in a matter of fact, P to the R Eisenstein polynomials are P to the R pure. However, I'm missing the fourth condition, because we can have a P to the R pure polynomial to be reducible. Let me give you an example. Okay, 2 to the 2. Okay. Let's not do this. Let me just do something easier. Okay, if you think about this polynomial. So this polynomial, if I take it as my prime is equal to 2, so this will be x squared minus 2 to the 2. So it satisfies the first two conditions, and actually the third condition also. But the fourth condition fails, because you have 2 and 2, their GCD is not 1. However, it satisfies this. So this is an example of a 2 to the 2 pure polynomial that is not irreducible. Okay? So 2 is for the prime I'm using, and this is for the power of the constant coefficient.
It's also not 2 to 2 Eisenstein.
Yes, because it fails the fourth. Yeah. Okay, so we can ask a valid question. What condition should I add to make a pure polynomial irreducible? Okay. Now, the fourth condition I should add is this. No wonder, the last condition. So if I remove this 2 and put something which is co-prime with 2 here, I will have an irreducible polynomial. Okay. Now, are all irreducible P to the R pure polynomial that satisfy this condition P to the R Eisenstein?
I don't get it.
Sure.
You wrote 4 over here. Are you adding a condition again to your definition, or is this
No, the thing is, like these 3 conditions,
PR pure?
P are pure, okay? If I have a 4th condition,
Then you get that.
you don't get that. You get something even more general.
Just to leave the 3rd condition.
Yeah.
Oh,
In a matter of fact, if you have these 4 conditions, we call the polynomial P to the R domain. And the polynomial will be always irreducible. If you miss this condition, you are not sure of the irreducibility of your polynomial as the condition here. Okay, so
sorry, so the period Dumas, that one is irreducible.
yes, it's also irreducible. It's a more general form of the Eisenstein. Okay, probably let me give you an example of a P to the R domain polynomial which is not P to the R Eisenstein. Let me maybe think about something. Okay, let me try to do it. Okay. If you think about this polynomial, now the GCD of 2 and 3 is 1. Now, and then if you try to do this condition, now the P-adic valuation of A0 here is 2. The P-adic valuation of A2 is 1. And the P-adic valuation of A3 is 0. And of course, I can neglect zeros. It's going to be infinity, so no problem with that. So my R over D here, so this will be my R. So my R over D here will be 2 over 3. And for this one, I will have the P-adic valuation of A2 over 3 minus 2, which is 1 divided by 1, which is 1. So this one is, since 1 is greater than 2 over 3, then it's actually satisfied. Okay? And so this is a 2 to the 2 Dumas polynomial. But it's not 2 to the 2 Eisenstein. Why? Because you have here a coefficient which is, its valuation is less than 2. Okay. So, it is the time now to introduce one of our first results.
By the way, Mohammed, I
Yes.
just want to say, you see where you wrote irreducible over Q at the very end?
Yes.
That space now is blank. We can't see them. Just that part.
Ah, okay, okay. Well, okay. So, we proved that P to the R domain are dynamically reducible. And we also proved that P to the R pure polynomials in general are eventually stable. Okay, so maybe let me do a sketch of the proof. Okay, so there is something more general that we proved. If now we are working in Q. However, these results can be extended in any, I would say, like algebraic number fields, for example. No problem with number fields because we can also divide primes. There's nothing very special about rational numbers here. Now, if f and g are p to the r pure, and I would say p to the r Dumas, both of them, then f composed with g is p to the r pure and respectively p to the r Dumas. Okay. So let us think a little bit about the proof. So here's a proof sketch. So if you let your f to be adxd plus a0, and your g of x to be bexe plus b0. Now, if it's p to r pure, then it satisfies the first three conditions. P-adic valuation of the leading coefficient is 0. Both of them, the p-adic valuation of a0 and b0 are r, and it satisfies also this. Okay, so the first thing we should prove that the p-adic valuation of f of g of 0 is actually r. This is the first step in the proof. And to show this, it's not very hard. So think about it this way. If you do f of g of 0, this is f of b0, right? So you will get ad b0 to the power of d, ai b0 to the power of I plus e0. Now let's think about the p-adic valuation of each expression here. So what's the p-adic valuation of this? So the p-adic valuation of ad b0 to the power of d is p-adic valuation of ad plus d p-adic valuation of b0. Now this is 0, and I know that this is r, so this is r times d. And the thing is, I did not stress on this point before, but we are not really interested in polynomials of degree 1, of course, because under iterations it will be very just transformations. Okay, so I know that this is greater than r. Now, if I think about the other, if I take one of these, so ai b0 I, this is the p-adic valuation of ai, plus I, p-adic valuation of b0. So this is p-adic valuation of ai plus I into r. And I know something about this, that it is greater than or equal to r over d times d minus I. So you get at the end r plus 1 minus 1 over d. Let me think about it. Yes, IR. Okay, which is actually greater than 1, or always. So if you have this to be greater than 1, and everything here is greater than 1, the p-adic valuation here is r exactly. So this sum, its p-adic valuation is greater than r. So the sum, whenever they are different, the sum is the minimum, it will be r at the end. Okay, to prove the other part, I don't want to, okay, I want to keep this one. To prove the other part, we try to take a monomial. So I can really think about this. AD BEXE plus B0, then to the power of D, and then AI BEXE plus B0 to the power of I, plus some stuff, and then we reach E0. So the thing is, the main idea is that if I take a monomial here, how will it look like? It will be something like BI, x to the I, and then I should actually multiply it by some exponent qi. Okay, now AD, its P-adic valuation is 0, so I don't really care about it. Now, if I multiply that, I will get BI Now, the thing is, if I multiply by B0, its P-adic variation is R, so I will be very lucky. So I would prefer to consider it without the P0. So I will have BI QI, and then X of I QI. Okay? So if I want to find how will the monomial look like, I will have this. I will have this. Okay? Now, if I think about the P-adic valuation of this, again, remember that f composed with g will be a polynomial of degree de. So we need to check that if this is, let's say, c, it's a monomial in my expansion. So I need to check that P-adic valuation of c over de minus I is greater than or equal to r over de. Okay, so the thing is, well, we did it by contradiction. You can, if you go the papers on archive, you can check the proof. So yeah, this is the main idea. Okay, so what else? Now, we might actually have a, we might like ask this question. Okay, so we already know that if the composition of a P to the R Dumas is a P to the R Dumas, which is irreducible, so that's fine. But I did not really say about why the P to the R pure will be eventually stable. Now, there is actually a fact due to Jacquard. It says that a P to the R pure polynomial has at most GCD, say of degree D, has at most GCD of D and R irreducible factors. Now again, this comes from Newton polygons. So when it's 1, that's why it's irreducible. Okay, so if I take the iterates of a pure polynomial, what will happen? So for F1, I need to, now this is the number of irreducible factors. Now, note in F1 it's degree D, so it has GCD of D and R. Again, R is the P-adic valuation of the constant coefficient, and D is the degree. Now, if I go to F2, I should consider GCD of D squared and R. We already proved that the constant coefficient of the second of any iterate will be R from the previous fact. So if I go like this, I will have Fn. It should be the GCD of D to the n R. Now this set is actually finite because it's always less than R. So we will be able to find, so in general, the number of irreducible factors will not be beyond the maximum of this set. So that's why it's eventually stable. Okay. Okay. Let's ask a different question. Now,
You want this to at some point become 1.
no, the thing is, if it's 1 from the beginning, then it will always be 1. Now, if it's greater than 1, then I cannot use the criteria that I mentioned to judge if it's irreducible or not. So the thing is, I cannot say anything about the dynamical irreducibility, but I can say something about the eventual stability. Eventual stability means that the number of reducible factors of any iterate is bounded above. So,
Oh, that's it. Okay.
yeah, yeah. So, okay. So let's ask the following question. Can we characterize the set of all f's such that f is not p to the r pure, but fn is p to the r pure. So after some iterates, I can get my a certain iterate to be p to the r pure. You can think about it as respectively p to the r Dumas and respectively p to the r Einstein. In these two cases, it will be dynamically reducible. And in this case, it will be also eventually stable. Is that clear, or I need to? Okay, so you agree that if f is dynamically irreducible, if and only if fn is dynamically reducible. So if I take any iterate of f, if all of them are irreducible, this means that any iterate of f to the n is will be reducible. Now, same thing if I take f to be eventually stable, so the number of reducible factors do you agree? So here the number of reducible factors of any iterate of f is bounded above by some c. So fn itself, it's bounded above by c, and any iterate of fn is bounded above by c. Now similarly here, because you can actually get some sort of like common iterates. Okay. So can we characterize these polynomials? In a matter of fact, we do have a complete characterization. So let me explain it. Let me say this and then probably take your questions. Yes. Okay, so if f is not p to the r pure, but fn is, so f is not p to the r pure, but fn is p to the r pure for some n is greater than 1, if and only if. Now the degree of f, as usual, is equal to d, and f of x is again e dxd plus a0. Now d, if and only if all the following happens, d is a power of p. The P-adic valuation of a0 is equal to 0. And the AD, sorry. There exists a C in Q such that f of x plus c is p to the r pure. Okay? So in this case, yeah, let me add something also. Okay, so we just don't want the P-adic valuation of the element of the coefficients in the middle to be less than 0, because the shifts will not be 0, like if Okay, so let me give you an example. If you,
I got a question before you read that.
sure, yeah,
So this sequence that you just wrote,
yes.
it doesn't necessarily have to choose one itself.
No. If for the D, if it's not 1, then it cannot reach 1. But the thing is, if,
It's finite, right?
yeah, it's
Well,
finite.
If D is 1, it can't reach 1.
Yes.
But if it's not, so if it's finite, then there's only a finite number of options you can pick.
Yes.
And if two of them repeat, if you'd never pick one, then two of them have to repeat. If they do, then couldn't you say that if you divide so if you have D to the N, GCD of D to the N and R is, let's say, some B. Not finite, it's just B. And the GCD of D to the N plus some N and R is also B.
Yeah.
Then the GCD of D to the M and R is 1.
Not necessarily.
Okay, never mind. I don't know.
No, not necessarily. Yeah, like the thing is, what we care about from this set, it's that it's finite. Okay, so, and actually we know it's always less than or equal to R. Okay, so let me give you now a quick example. So if I let me think about that. Okay, there's something that I forgot. Sure. Okay, so the thing is, there is something also about the least n, such that n is p to the r pure. This is n is equal to, so it's actually the order of A0 in the multiplicative group modulo P if A is not congruent to 1 mod P, else n is P. Okay? So as you see here, we should have a power of a prime, and this, the P-adic valuation of the constant term should be 0. This should be 0, and it should be a shift of a p to the r pure polynomial. So if you really think about this, x squared plus 2x plus 3. Yes, plus 3. Now if you test f of 1 here, you will get it to be 1 plus 2 plus 3, which is 6. So actually, f of x plus 1, this is another way to say that f of x plus 1 is 2 Einstein. Okay? So from our theorem here, now P is 2, so always the second iterate should be 2 Einstein. Okay? I will just, what I need to check is just the constant coefficient, because everything here will be divisible by P inside, divisible by 2. And the leading coefficient, it's not going to be divisible by 2. So the thing is, if you try f of 3, okay, that's not going to be, okay, let's take it modulo 4. So 3 squared.
So I do want to say we're almost at 4.
Okay.
So if you want, we can stop at this example.
Okay, sure. Sure, like I'm almost done, like that's it. Okay. So the thing is, yeah, so maybe, okay, you can do that. You can actually, f of 2 is 2 Einstein. Check it yourself. Okay? Okay. That's it. Thank you for listening.
Okay, thank you.
Okay, thank you so much. Thank you.